Hello, and welcome to this video series on algorithms. This is part 8 of Module 4 on greedy algorithms. In this session, we will study the interval scheduling problem. Imagine you are managing a single-threaded server over a time interval scaled from 0 to 1, as shown on the horizontal axis. Because the server is single-threaded, it can run only one job at a time. Assume jobs cannot be preempted once they start. Each job request comes with a start time and a finish time, which define the time interval during which it needs the server. In the example on the slide, the blocks labeled A through F represent 6 submitted jobs. The numbers in brackets next to each job give its start and finish times. As the server manager, you must choose which jobs to run so that no two accepted jobs overlap in time. Your goal is to maximize the number of accepted jobs. For example, in this schedule, you can accept jobs A, C, and E. These 3 jobs do not overlap in their requested intervals. In this configuration, you cannot add any other job without creating a conflict. This problem is known as the interval scheduling problem, and it appears in many real-world settings. For example, we can use it to maximize the number of meetings scheduled in a single conference room. We can also apply it to maximize the number of signals transmitted through a fixed communication channel. Airports use the same idea for runway management, where the goal is to schedule as many takeoffs as possible without overlap. Now, we introduce the formal definition of the interval scheduling problem. The input is a set of intervals I. Each interval I has a start time Si and a finish time Fi. The goal is to find a subset A of these intervals that is as large as possible, subject to the constraint that no two intervals in A overlap. We call such a subset A a feasible set. Here, we allow one interval to finish at the exact time another interval starts. If this rule needs to be changed, the algorithm can be modified easily. Let's consider several possible greedy strategies and intuitions behind them. First, we might try selecting the jobs with the shortest running time. The idea is that shorter jobs may allow us to pack more intervals into the schedule. Second, we might try selecting the jobs with the earliest start time. This approach attempts to keep the server busy as soon as possible and avoid idle time. Third, we can try selecting the jobs with the earliest finish time. The intuition is that finishing earlier leaves more room for future jobs. Let's test each strategy using simple counterexamples. First, consider the shortest running time first strategy. In the example on the slide, job A has the shortest duration. If we schedule job A, we can no longer schedule jobs B and C because their intervals overlap with A. However, we can schedule both jobs B and C together, and they do not overlap. So, the optimal solution here is to accept B and C, not A. This shows that the shortest running time first strategy does not always produce an optimal schedule. Second, consider the earliest start time first strategy. In the example on the slide, job E has the earliest start time. If we accept job E, its interval overlaps with jobs A, B, C, and D. However, we can accept A, B, C, and D together as a larger feasible set. That schedule is clearly better than choosing E alone. Therefore, the earliest start time first strategy also fails to guarantee an optimal solution. Finally, we are left with the earliest finish time first strategy. Here is the pseudocode for the algorithm that uses the earliest finish time first strategy. In line 2, we sort all jobs in ascending order of their finish times. In line 3, we initialize the accepted set A to be empty. We also define a variable current end to track the finish time of the last accepted job. We set current end to -infinity at the start. In the for loop beginning at line 4, we examine each job in sorted order. For each job, we compare its start time with current end. If the job start time is greater than or equal to current end, then it does not overlap with the last accepted job, and we can accept it. We add the job to A and update current end to the job's finish time. Otherwise, the job overlaps with an accepted job. We skip it. Let's walk through this algorithm with a simple example. Consider the jobs A through G and their time intervals shown on the slide. First, we sort all jobs by their finish times. The slide shows the resulting order, with each job labeled by its position in the sorted list. Then, we set current end to -infinity. On the slide, this is represented by the yellow arrow positioned before all intervals. We now check the job with the earliest finish time in the sorted list, which is job A. Its start time is 0.02. Since 0.02 is greater than current end, which is -infinity at this point, there is no conflict. In this case, we can accept job A and update current end to A's finish time, 0.2. Next, we check the second job in the sorted list, which is job B. Job B's start time is 0. Because 0 is earlier than current end, it overlaps with job A. Therefore, we cannot accept job B. We then examine the third job C. Its start time is 0.23, which is later than current end. So there is no overlap. We accept job C and update current end to its finish time, 0.35. The next job in the sorted list is E. Finishes earlier than job D. E's start time is later than current end, so it does not overlap with the previously accepted jobs. We accept job E and update current end to its finish time, 0.48. We then consider job D. Its start time is earlier than current end, so it overlaps with job E. Therefore, we skip job D. Next, we check job F. Its start time is after current end, so it does not overlap with the previously accepted jobs. We accept job F and update current end to F's finishing time. Finally, we check job G and reject it because it overlaps with a previously accepted job. The algorithm, therefore, accepts jobs A, C, E, and F. You can verify that this set is a maximum feasible set. There is no other schedule that accepts more than 4 non-overlapping jobs from the given intervals. Next, we will prove that the earliest finish time first greedy algorithm is correct. We will do this by establishing 2 key facts. First, the algorithm always produces a feasible set. No 2 accepted jobs overlap in time. Second, the algorithm produces a maximum size feasible set. No other schedule can contain more accepted jobs. First, we show that the algorithm always produces a feasible set. By design, the algorithm accepts a job only if its start time is greater than or equal to the finish time of the last accepted job. This condition guarantees that the new job does not overlap with any previously accepted jobs. Therefore, all accepted jobs are non-overlapping, and the algorithm always produces a feasible set. Second, we show that the greedy algorithm maximizes the number of accepted jobs. We compare the job set A produced by the greedy algorithm with a hypothetical optimal set O. Let A contain K jobs and O contain M jobs. We can sort the jobs in O in ascending order of their finish times. In this case, we write AI for the ith job in A and OI for the ith job in O. With this notation, we will show that for every index I less than or equal to K, the finish time of AI, denoted FAI, is less than or equal to the finish time of OI, denoted FOI. In other words, the ith job chosen by the greedy algorithm finishes no later than the ith job in the optimal solution. We prove this by math induction on I. First, consider the base case where I equals 1. We claim that the finish time of A1 is less than or equal to that of O1. By the algorithm, A1 is the job with the earliest finish time among all jobs. Hence, it must finish no later than any job in O, including O1. Next, we state the induction hypothesis. Assume that for some index x greater than or equal to 1, the finish times satisfies FAX less than or equal to FOX. The figure on the slide illustrates this assumption. The xth job in the green greedy set finishes no later than the xth job in the red optimal set. It assumes that the x block in the green set finishes sooner or at the same time of the x block of the red set. This is the condition we will use to prove the statement for index x plus 1. To extend the hypothesis to index x plus 1, first recall that we have FAX less than or equal to FOX directly from the induction hypothesis. Since the optimal set O is feasible, the job OX plus 1 must start after OX finishes. Therefore, its start time SOX plus 1 is greater than or equal to f(0x) as well as f(a)x. This means that ox plus 1 does not overlap with any drop in a up through ax. So, at the moment when the greedy algorithm selects ax plus 1, ox plus 1 is also a valid candidate and could be selected. In this case, even if the greedy algorithm has no better choice for ax plus 1, we can at least accept ox plus 1 into a, thus making f(ax plus 1) less than or equal to f(ox plus 1). This completes the induction step. As a result of the induction, for every index I less than or equal to k, ai finishes no later than the job oi. With this property, we can now compare the sizes of the greedy set A and the optimal set O. Recall that A contains k jobs and O contains m jobs. We claim that k cannot be smaller than m. Recall that we have proven that FAK is less than or equal to FOK. Because O is a feasible set, job OK plus 1 must not overlap with any job in A up to AK. Thus, when the greedy algorithm encounters OK plus 1, it should have accepted this job. But this contradicts with the assumption that A contains only k jobs. Therefore, k cannot be smaller than m. In other words, the greedy set A is as large as any optimal set O, and is therefore optimal. Finally, let's analyze the time complexity of the algorithm. Let n be the number of jobs. Line 2 sorts the jobs by finish time, which takes O n log n time. In line 3, initializing the set A and the variable current end takes constant time. In line 4, the for loop examines each job once, running O n iterations. Inside the loop, checking start and finish times, adding a job to A, and updating current end all take constant time. Therefore, the overall time complexity is O n log n, dominated by the initial sorting step. In summary, we presented a greedy algorithm for the interval scheduling problem. The greedy algorithm follows the earliest finish time first strategy and runs in O n log n time. A common variant of this problem is weighted interval scheduling, where each job has an associated profit, and the goal is to maximize total profit rather than the number of jobs. This weighted version does not admit a greedy solution, but it can be solved in polynomial time using dynamic programming. If you're interested, you can watch the corresponding video in the dynamic programming module. Thank you for watching, and see you next time.